Hi everyone, and welcome to part 3 of the respiratory system. In this session we're looking at respiration and ventilation processes. Pulmonary ventilation refers to breathing, and pulmonary means related to the lungs. External respiration, as we learned in our previous session, refers to the transfer of oxygen and carbon dioxide between the inspired air that is breathed in, and the pulmonary capillaries. Internal respiration refers to the transfer of oxygen and carbon dioxide between the capillary red blood cells and the tissue cells. There are two phases of pulmonary ventilation. The first is inspiration, also known as inhalation. This is where the air is breathed in. And the second is expiration or exhalation, where the air is breathed out. Mechanical forces cause the movement of air, and this is where the laws of physics will apply, as gases will always flow from areas of high pressure to areas of low pressure. This movement of gas from areas of high pressure to low pressure sets up a pressure gradient. The movement of air into and out of the lungs is governed in part by Boyle's law, and this refers to the volume of gas will vary inversely with pressure, assuming that the temperature is constant. This can be written as P1V1 is equal to P2V2. Atmospheric pressure, or the pressure of the gas around us, is at sea level approximately 760 millimeters of mercury. For air to enter the thorax, the pressure of the air in the thorax must be lower than atmospheric pressure. Making the volume of the thorax larger means that the air inside it is under less pressure. The air has more space for the same amount of gas particles, therefore the gas particles are under less pressure. Movement of the diaphragm and the intercostal muscles help to accomplish this. During inspiration, the dome-shaped diaphragm, which sits at the base of the lungs, flattens as it contracts. This increases the height of the thoracic cavity. The external intercostal muscles contract to raise the ribs, and this increases the circumference of the thoracic cavity. So together, the ribs become elevated as the intercostals contract, and the diaphragm moves inferiorly during contraction, increasing the height of the cavity. The intercostals keep the thorax stiff so the sides don't collapse with the change in the diaphragm's position. During deep or forced inspiration, additional muscles are recruited to this process. It is not essential to know these. However, where a patient may be suffering from respiratory distress, some of these accessory muscles may be visible to the observer as the patient is working harder to breathe. So this diagram shows the relative position of the chest and particularly the diaphragm during breathing in and breathing out. You'll be able to see that when the patient has breathed out, the thoracic cavity is smaller, whereas when they breathe in, the thoracic cavity is larger. The chest wall expanding increases the size of the thoracic cavity in the lungs, and the pressure in the lungs drops to about 758 millimeters of mercury, creating a negative pressure gradient, and this results in airflow into the lungs. As the pressure becomes equal with atmospheric pressure, the thorax stops expanding and the airflow stops. And as we've said, during forced inspiration, accessory muscles are recruited in order to increase this volume. This diagram from your textbooks explains the previous slides. Quiet expiration in healthy people is chiefly a passive process. There is relaxation of the inspiratory muscles. The rib cage drops under the force of gravity. the diaphragm relaxes and moves upwards, and elastic fibres in the lungs recoil. Consequently, the volume of the thorax and the lungs decrease, and this increases the pressure, forcing the air out of the lungs. Forced expiration is an active process which requires contraction of the abdominal wall muscles, leading to an increase in intra-abdominal pressure. This forces the diaphragm superiorly. The rib cage is depressed, thus decreasing the thoracic volume. It may be helpful if you try to do a forced exhalation in order to feel the different muscles acting in this process. So as we've said, the chest wall and the diaphragm relax. The elastic recoil of the chest wall and the lungs causes the space within to decrease. Due to the decreased space, the pressure in the lungs is increased to about 762 millimeters of mercury. Pressure gradient results in airflow out of the lungs. And as the pressures become equal, the gas movement ceases. This diagram from your textbooks explains this process. Compliance is a term used to describe the ease with which lungs and thorax expand during pressure changes. Greater compliance implies greater ease of expansion, and any condition that destroys lung tissue, increases fluid, decreases surfactant, or impedes lung movement will decrease compliance. Diseases which decrease compliance also increase the energy required for breathing, and these include asthma, emphysema, and bronchitis. So we can see in a normal lung on the left-hand side the normal shape of the alveoli. The image on the right-hand side shows a lung with emphysema. There is a marked reduction in the number of alveoli with large gaps. This is the effect of reducing the available surface area for gas exchange. Factors that increase energy include loss of pulmonary surfactant, an increase in airway resistance, or a decrease in pulmonary compliance. We've mentioned the term surfactant before in our previous session. The lung's surface tension causes the alveoli to assume the smallest diameter possible. Alveoli have a natural tendency to collapse in on themselves, and surfactant helps prevent this collapse by decreasing the surface tension. As we learned in our previous session, type 2 epithelial cells within the alveoli produce surfactant, and it's a detergent-like substance secreted in fluid-coating alveolar surfaces that decreases the surface tension. Without surfactant, the walls of the alveoli would stick together during exhalation. If surfactant production decreases, for example during pneumonia, high pressures may be required to maintain lung expansion. Premature babies tend to have difficulties breathing, largely because they lack surfactant within their lungs. The elastic forces of the lung oppose lung expansion. However, much of the resistance to the flow of air is encountered in the upper airway, for example the nasal passages, 50%, the mouth and trachea, between 20 and 30%. Resistance may increase substantially during increased ventilation, for example during exercise. It falls dramatically at the bronchial trees, however secretions or constriction can increase resistance. This slide shows the difference between an inflamed bronchial tube of an asthmatic and a normal bronchial tube. We can see the image on the left shows a much narrower airway with secretions. This makes it much more difficult for the air to move, i.e. the resistance is increased. In our next session, we'll be looking at lung volumes and capacity.